we got to know what is 1 plus A beta, the amount of feedback and loop gain, and the importance of 1 plus A beta as it was involved in all the all the benefits that we named here about the negative feedback. So in stabilizing the gain, that factor plays a role. The gain with feedback will change less than the gain without feedback by a factor of 1 plus A beta. And based on the same fact that we mentioned up here, we will get more linear systems, and we have more bandwidth again by the factor of 1 plus A beta. Then we mentioned that we need to know about two-port networks, so we reviewed Y parameters, Z parameters, H and G, as we are going to use them. We were going to use them in feedback networks like this, that we have basically two-port networks that are connected either in series or parallel on the input side and output side. So if it is series on the input, shunt on the output, it's series shunt. If it is shunt on the input, series on the output, shunt series, and series series, and shunt shunt. Now, for each one of these, we did have examples and everything, but before that, we revisited actually the old friend non-inverting amplifier, and we compared it with when we had assumed that the op-amp is ideal, everything was either infinite or zero. With when there was at least one non-ideality in this op-amp, that gain was an infinite, and we realized the difference isn't much really when we study this under feedback and the feedback theory. And we also showed that if we change the open loop gain by 20%, the gain under feedback changes only by 0.02%. So this was important observation and confirmation to what we had mentioned before. Then we started getting into the details of each topology. So series shunt was the first one that we started talking about it. We started with ideal situation. And in ideal situation, we have, for this case, for series shunt, we have a voltage amplifier, and therefore the model inside this amplifier must show that. And the feedback network reads the output voltage, so it must be like a voltmeter with infinite input resistance, but also it produces a sample of that voltage using this dependent voltage source. And there is nothing else, no RS, no RL, nothing else. So this was the ideal situation, and this ideal situation very much is like the very first block diagram that we looked at. Sorry, I have to keep rolling up. Oh, that's too much. But anyway, yeah. Okay, that was a mistake, but I did it. Okay, here it is. It's just like this. Okay. Now, if on the input side they are in series or shunt, and on the output side the same way, shunt or series, makes different cases. But basically we are doing the same thing. Okay. Let me see how fast I can go back. Oh, too fast. Okay. So that means that we can apply the formula AF equals A over 1 plus A beta to a system like this, which is ideal, right? And just a moment. And also we considered the two systems, the two blocks amplifier and the feedback network be unilateral, which means the signal moves in one direction, left to right in the amplifier, right to left in the feedback network. So that helped. That helped in idealizing the feedback network. But then we also looked at the input resistance when it is in series. It gets multiplied by 1 plus A beta. What gets multiplied by 1 plus A beta? Ri, which is the input resistance of the original amplifier that we had. Okay, so this is the original amplifier. This whole thing is the amplifier under feedback with the feedback network, right? And also we looked at the output and realized that it is actually, because we have shunt, it must be divided by 1 plus A beta. So all that, and finally we could draw the model for this entire amplifier with feedback, the whole thing. Okay, the same way, just like what we had for the amplifier, the original amplifier. So this was the ideal situation. Then we looked into non-ideal situation. What do we have extra in non-ideal situation? First of all, we do have an RS and we do have an RL. And inside the feedback network, depending on which feedback network we choose, and we have to choose the proper one, the one that has series on the input side, shunt on the output side, so that we can actually absorb the resistances inside the feedback network back up into the amplifier. And in fact, by doing so and ignoring this source due to unilateral behavior of the feedback network, we were able to make it look like ideal situation. Now, if we had the gain of the amplifier, the gain of the newly formed amplifier, then we could use the ideal formula, the ideal situation formula that we had for the system as well. So basically, in all these cases, we end up absorbing the extra resistances into the amplifier so that the feedback network is ideal, and then it's attached to an amplifier, and therefore it is looking like the ideal situation. Finding the gain of the amplifier and finding the beta properly, then we could use the formula for AF equal to 1, AF equal to A over 1 plus A beta. Then we went into an example, again, the old friend non-inverting amplifier op-amp. And well, we first identified where the loop is, what is the feedback network, and then from that we had to find R11 and R22. Okay. We also brought the R11 and R22 into the amplifier, formed the newly formed amplifier. We had to find the gain of it, and also from the feedback network we had to find beta, put them together in this formula, and we had the gain with feedback. Input resistance we had to find, output resistance we had to find. Then we would multiply the input resistance by 1 plus A beta, divide the output resistance by 1 plus A beta. That would give us the output and input resistance on the feedback. However, neither RF nor RL were not a part of the amplifier. So we had to take them out. It was easy on the input side because it's series. We would simply subtract it from what we had found as RIF. For the output side, it was a little painful, but I believe and I hope that we know how we did it and what to do. It is actually expressed better here. So it is like, you know, we have the RL with the desired output resistance with feedback that we call the parallel of them ROF. So in order to get to R out, we have to take RL out of the belly of ROF. And that is done just like this. And it's very likely that we have an exam question related to this. Okay. Series shunt. Series shunt was. Oh, it is still series shunt, which is the second example for series shunt. This was a good example too. We found the feedback network. We basically made the R11 and R22, brought it into the amplifier. It was a two-stage amplifier, so this became the newly formed amplifier. The gain of it was easy to find if we knew Hawaiian bands, and we could actually realize what we have on the emitter side as well as the collector. No. So we found the gain of this amplifier, its input resistance, and the output resistance, which was a little more tricky. But when we looked here at this node, what we saw up there was the reflected version of this to the emitter next to the little RE, going to the ground. So from this node, the series of those two were going to ground, as well as the 2K and the R22. So that was the output resistance. And then we also found beta, put it together with the amplifier gain, found the gain with feedback, input resistance under feedback, multiply 1 plus A beta, and then for output with feedback, divide by 1 plus A beta, take the RS and RL out, then we had true output resistance with feedback and true input resistance with feedback. Okay, so R in and R out, the way that we find after extraction of RL and RS is what we call true input resistance with feedback. So that ended there, and that was the first and the most important one. When you do something for the first time, it becomes important, because if you learn what we did and you learn the trend, you can apply to other variations of feedback networks. The other variations are the other three topologies, and we exactly do the same thing. So then we went to series. And in series, we had transconductance amplifier. We had the transconductance amplifier. In an ideal situation, we could use all the formulas that we know about it. Here, we still didn't know that on the output, when we have things in series, what happens. And then we proved ourselves that just like input, it gets multiplied by 1 plus A beta. And again, that was another proof of importance for the 1 plus A beta, or the amount of feedback. Then we moved on to the real case. Again, we tried to idealize the feedback network by absorbing the resistances up in the amplifier and killing that extra source. This is what we had as the newly formed amplifier, idealized situation for the feedback network. It was easy to take RS and RL out, because in both sides we have series, and it is sufficient to subtract RS and RL from input and output resistance. So ideal, newly formed amplifier, R11 and R22 are absorbed into it. We find beta. That is exactly the same way that we treated series shunt, but here, because we have series, things are going to be different. The feedback network is Z parameters, and we have to find the beta accordingly, and the amplifier as well. Went to the example that we had 3-stage amplifier, found the feedback network, and then we found R11, R22, brought it into the amplifier, newly formed amplifier. It is very likely that I ask you just find the newly formed amplifier. So if I ask you to sketch the newly formed amplifier, it doesn't mean to find the voltage gain. or any gain, okay, of the amplifier. If I'm asking you just to sketch, this is what I want. I want you to go from this to this, okay? That's all. But if I ask you to find the gain of the newly formed amplifier, then you have to go through the process of finding the gain of each stage, put them together like this, and of course, that would give you the gain of the loop. And for series, it is I/O over VI, I/O of the loop, okay? And the output of the loop could be different than the output of the circuit. This is the output of this circuit, okay? Of course, we are often interested in finding the gain, the voltage gain of the circuit. Then we have to find VO over VS. But as far as the loop is concerned, it's an I/O over VS. So we put everything together. We found the newly formed amplifier gain. We found the feedback factor, the beta. And we had to find the current division of the output current on these two branches in order to get the VF over I/O. And then when we have beta, and we have the AF, the corresponding AF, which is the transconductance gain on the feedback. Now, if we wanted to go to the voltage gain of the circuit, because the output voltage was simply related to the output current of the loop, and in fact it was actually almost equal to that output current, we would have to multiply this RC3 by that current to get the output voltage. So in AC, that's how the output voltage is made. So the gain that we found, the transconductance gain that we found, if we multiplied by RC3 in the numerator, then that would give us VO. So basically the AF must be multiplied by RC3. So we found the voltage gain. Again, input resistance and output resistance was also found. Output resistance was a little tricky, again, because when you break this link here, then you have to look both ways. One is to the ground down here, and the other one to the ground from up there. And once again, you had to consider this RC2 reflected back on the emitter side. Going to ground, through the ground, it's in series with this R22 when we are looking into these two. But soon we realized that if we follow that, and then there will be an output resistance that we have to multiply by 1 plus A beta, by the way, and then that fits in the loop as the output resistance under feedback of the loop, which is underneath the emitter terminal of the transistor. From our experience before in current sources, we had the relationship that we needed for finding the resistance that we view into the collector of a transistor whose emitter is in series with an external resistance. Okay? And we followed that, we got a huge resistance. But the point was that we really didn't need to find this resistance, because this huge resistance is from collector of this Q3 all the way down to the ground, and it's huge. So from up there we have RC3 connected to ground as well. Parallel of the two is going to be the smaller one. So we really didn't need to do that. But just to prove to ourselves, we did it, and it was a good practice, an exercise. In fact, we need to be able to do this kind of, to find the outputs resistances like this, or the input resistance. Anyway, so that ended the series. You guys are very quiet. Are you hearing me?
Yeah, we can hear you.
Oh, you do? Okay. So I take it that everything is clear. Is that right? Because I expect you to pause me if there's anything that, yeah, Aiden.
Then I would just want to ask a quick question of, so in the past when we were grabbing, it looks like we're grabbing, because this one is series and it's not directly connect the input that we're going for, because we're saying it's series, or sorry, the output anyways, my bad. The output that we're connecting to say that it's series, because it doesn't line up with the output of the actual circuit. Is it because of that now we have to, is it because of that we have to find two output resistances? We have to find the output of the loop and the output of the actual circuit. Otherwise, if they were connected at the same point, we would just we would only need to find the output of the loop and subtract any.
Yeah, if our output was coming from here, if this was the output, then the network was shunting. It was shunting on the output. And then the network, the feedback network, would become this and this. Just like the non-inverting op-amp amplifier. Okay? So in a way, yes. I mean, that's a good observation. When we are not taking the output from here and the output voltage. So, and here is the loop, So if here is the loop and we are not taking the output voltage from there, it must be the current that we are interested in. If that is what you were trying to deduce. But yes, more or less that is right. So, Aiden, did you just raise your hand, or is it before?
I'm just trying to confirm, because I was trying to go over all the examples before class, but I'm still having an issue in some cases determining based off of the circuit whether or not it's series shunt or series.
Sometimes it becomes tricky, yeah.
Just because
because
in this case, for this example in particular, knowing if it wasn't for the fact that you have the arrows being outlined through the positive I out and V out, I might think that this is connected differently than a series, or that the output at the bottom could actually be that there could actually.
But if you compare this with say this, it's very much like that one, except instead of the differential pair, we have two other single transistor amplifiers, right? And the output, instead of going out from the collector, is going out from the emitter. And here it is. You see, this is like RE2, and this is RF and RE1. So this could very well, if we weren't taking the output from here and we were taking the output from the collector, this is exactly that same circuit. Okay, and so what I'm trying to say is that if you compare just the examples that we have used, if you compare them and look at them accurately, you can see the differences, and you can always basically come up with the right decision about what kind of feedback it is. You see, here it is obvious that we're tapping on the output voltage when our feedback network is attached to the output voltage. Okay, so it must be a voltage, and when it is a voltage, then it is the shunt on the output side. But in the other one, we are not doing anything with the voltage. And as you said, yes, the voltage is elsewhere that we are interested in. So this must be that. You could say for yourself, this is a voltage, and if I were interested in this voltage, then this resistance would become a part of this amplifier. And now this would be the feedback network, okay? But what this would give you would be this voltage over the input voltage. Now, again, if you want to relate this voltage to the output voltage, you have to convert it to the current, and then again, back here to the voltage, So it's kind of a double work if we wanted to go that way. But directly, when we don't see any voltage of importance here, and we have a loop, so it must be the current. And then we can relate that current to a voltage elsewhere as we are interested in. Hope that helps.
I believe it does in terms of answering that question, just in terms of, because so I guess I just have to keep going over some more examples, just because sometimes identifying whether or not, because I still sometimes have problems just understanding why it is specifically.
No, that is natural. That is natural, but you need to give it a second thought always. When you say, "Oh, is it series, or is it series shunt, or whichever?" Just give it a second thought, and hopefully you will verify your first thought.
I tried it in the tutorial was all, and I was going to come to you to office hours, but I was a bit unfortunately busy. Something came up because in office hours, they are in the tutorial that we went over where it had 3-stage amplifiers. The tutorial was assuming that it was series, when to me it looked the same as the original up amps we did, just now it's 3-phase. And because it looked like it was connected the exact same way.
Sorry, which problem in tutorial you're talking?
It was the 3-phase tutorial. It was the 3-phase amplifier that we covered in the most.
The 3 op amps?
Yeah, I believe that was. I thought it was series or shunt. Sorry, series shunt. Shunt again.
I think it is series shunt, because it is eventually, if I'm not mistaken, I don't remember the details of it, but it is the feedback was like the feedback of the non-inverting amplifier, wasn't it?
Yeah, no, it's exactly the same, and that's why I thought it was. And then she said it was series, and I lost, and that was where I kind of.
She said series. Okay, so I don't want to spend this time doing that because I have to finish this. If we finish this and we have extra time, then I'll go look at that. But if not, then I'll do that and let you guys know next time. Which it is, and if she said it is series, then we have to change that. Yeah, but does she write it on the tutorial? This thing?
I don't believe she wrote it. It's just when I asked her, she said she.
Oh, when you asked her? Okay. Yeah, that's okay. We will figure it out. So let me continue and hopefully finish the feedback, and then if you have any questions like that, we can explore that. However, if you have any questions regarding what I'm going over, also please ask as Aidan did. I want you to have no questions left with the feedback, because as I said, after this, I'm not reviewing it. Of course, I will answer questions if you have, especially if you come to the office hours. But generally, I wanted to put this aside, and we've spent so much time on it. We should have a good understanding and ability to deal with the feedback circuit. Yes. So shunt, we had parallel on both sides, input and output, which meant both input resistance and output resistance must be divided by 1 plus A beta. However, the gain is always A over 1 plus A beta, except this gain now is a trans-resistance amplifier. So it is a gain of the voltage over a current. Okay, so this is true for the loop. Whatever the loop demands, which is a voltage over a current, and it follows this formula, same formula for all of them. When we jumped into the real case with RS, RL, and Y11 and Y22, which are resistances, inverse of resistances, basically. So once again, we had the newly formed amplifier and how to find R11 and R22, then incorporate it into the amplifier, the newly formed amplifier, find the beta properly, for finding the beta, even for finding R11 and R22, at the very end, when we reviewed the feedback, a small review, we did give tips, and we'll go over that again. So you don't really need to know or worry about the two-port networks, remembering how to find R11, R22 for each one of them. Okay, so you can formulate it. And that's done at the end of this series of notes. So and then we went into the example, or the first example. I think there is another one, maybe, but the first example was just basically a collector to base feedback single transistor amplifier. We realized that in this loop, it seems like it is taking the voltage on the output. So that's obvious that the output is connected to this resistance. But on the input side, it comes to a node, which means that it must be actually bringing the current in. So this resistance and a line of ground. So this is the input and output of the two-port network feedback circuit, which the other part of it is aligned to the ground. Let me see if I can. Did I do that? Oh, I have. Yeah, here it is. Yeah. So ignore this short. A line which is connected to ground down below, and the RF. This is the two-port network of the feedback network. So we realized that, but before we get to that, we had to do some DC analysis on this circuit. It started from what we know, and that is the 0.7 volts here. So it gave us the current and the voltages on the entire circuit. Then we went to AC, okay? So you see this GM, you need IC to come up with the GM that is here. You see the RPi, you need the IB for that, okay, to find the real value of RPi. So after DC analysis, we first draw the AC equivalent circuit of it, but then we had to change that to the newly formed amplifier by finding R11 and R22, absorbing it into the newly formed amplifier, and then finding the gain and input and output resistance of the newly formed amplifier, as well as using the feedback network to find the beta of it. And in this case, it was 1 over RF, negative of it. So we had beta, we had A, we used AF being equal to A over 1 plus A beta, which would give us VO over IF for this amplifier. Now, if we were interested in VO over VS, again, VS is IS times RS. In fact, we actually found this from here by converting this VS and RS to a current source, which is VS over RS and RS. So obviously, if we are looking for VS, we can multiply IS by RS. And since in our gain that we found, we do, have IS in the denominator. If we multiply it by RS, we get VS in the denominator, and we have V over VS. The input resistance and output resistance we had to find, and it was relatively easy, parallel combination, and we didn't have an RL, so we don't have to extract anything from what we find here, but on the input side we did have RS, and therefore we had to take it out of the RIS. I guess I'm not showing it here, right? I don't think I have the result of Rin, but in order to find the Rin, we have the RIF and we have the RS. We need to perform this. Yeah. Okay. Then there was another example of shunt. I will let you guys go over it. This one, the feedback network was this T connection of the resistances, which is this. We found beta from it, also R11 and R22, and attached it to the amplifier. So this was the newly formed amplifier. And we found beta as well. Having them, we could find the gain, AF, which is again V over IS. And we did the rest of the things exactly the same, RI, RO, and in this case we had RL, so we had to take it out to find the R out, the true output resistance, as well as the inputs RS that we took it out in order to come up with the true input resistance of the amplifier. So shunt finished here. So up to this point we had 3 of the 4 topologies down, and only one left, shunt series, that we went over it last time. In shunt series, input is shunt and output is series. Ideal situation versus real situation, the only 2-port network left was G parameters, so we used it, and we found R11 and R22, absorbed it into the amplifier, made the newly formed amplifier, as well as beta. And then when we had A and beta, we could do a lot of things. Everything was determined. Then we came to this example. We ran a DC analysis first, as usual. Simply here, we assumed beta is infinite for the DC. And then we drew the AC small signal model of the entire circuit, and then we took this feedback network and found R11 and R22, absorbed it into the amplifier to form the newly formed amplifier. Okay, found the gain IO over II by following the current coming from input, making this voltage. This voltage comes to the other side, and then in the shape of a current, drop a voltage here. This voltage comes here as the current goes through these resistances, and it gives us I over II. Input resistance, basically the parallel combination of these resistances. And for the output resistance, again, like that other, the other series on the output series connection, that, you know, we had to reflect back the resistances that we had in the collector of the previous transistor into the emitter. And this is what exactly we've done here, but at the end we realized that it's not really necessary because it becomes so big that we don't really end up using it. Do I see Kishan has hand up? Yes, please.
Never mind. I was a little confused about the RE2 and RF. Like, why are they in parallel? But I think it's on the ones on the right side, not the ones on the
Oh,
left
this?
side.
Yes, yes,
Yeah.
that's here. Yeah, yeah, that's right. Okay, then from the feedback network, we found the data of the feedback. Again, we have 1 plus A data, we have everything. We have the input resistance with feedback, the output resistance with feedback, the gain with feedback, and then of course we related that to the gain of the collector of the resistance going through the RL over the input resistance, which was RS, and here is the big resistance that we find as the output resistance, which is useless because eventually the output resistance of the circuit is the RC2, the RC2. So that also ended the was it shunt series, right? And it was here that we brought everything together rather quickly and in a small scale. So we went over all these 4 situations. Also, we came up with like an instruction, you know, what we do one by one to deal with the amplifiers with feedback. But what was more useful was things like this that, you know, was telling us what do we mean by RI. The RI is the input resistance of the newly formed amplifier, which gets scaled depending on whether we have series or shunt at the inputs. Whatever that comes out is what we call RIF, but that's not the true output, the true input resistance with feedback. We had to extract RS to reach that Rin, which is the true input resistance with feedback. Same with the output resistance. The RO was the newly formed amplifier output resistance, which when it gets scaled, depending on series or shunt, we called it ROF. Then we had to take RL out before we would reach the true output resistance with feedback. Okay, so the 6 resistances, 3 input, 3 output that we introduced are all summarized here. So this is good. Also, we related the name of the topology, series shunt, series, whatever, to a way of finding R11, R22, and beta. So for R11, we look into the port 1, right? What am I supposed to do with port 2? Well, if it is on the output side, it says shunt, then we need to short it. Here is the short. When we look for R22, we're looking to the port 2. What do we do with port 1? Because we look into port 2, port 1 is under series. Series must be open. So series is translated to open, shunt is translated into short whenever we don't know what we need to do with that port. Okay. And in terms of finding the data, on the input side, whatever series mean would be true, open. So here it is. This is open here. On the output side, though, shunt meant voltage source. So it means that we have a voltage source. We need to consider a voltage source, and the VF over that voltage source will give us this voltage over the output voltage, give us the beta. So you can apply this understanding to all of these different topologies. Series, you want to look into port 1. Port 2, what do I do? Open. For R22, I look into port 2. What do I do with port 1? Open it. And for beta, as on the output side, as shunt was related to a voltage source, series is related to a current source. But on the input side, whatever series meant is the same series. Aiden, did you just raise your hand?
Oh, that was a while ago, so I was just going to let you finish first before I asked it because it was a question way up.
Oh, it is way up. Okay, and we are almost done with this. So in others, the same way, for shunt, wherever you need to do something with the other port is short, and short, and shunt meant voltage source for the beta. And finally, this other one, which is shunt series. Series means open, shunt means short. However, for the beta on the other side, series meant current source. Right? So, if you remember this, you don't really need to know what is the nature of this feedback network in terms of the two-port network. Okay? You just perform whatever this guides you to. Keep this open or keep this short, and you mechanically can find whatever that you're looking for that way. Okay, now Aiden, what is your question?
It was just if you could scroll back up to the current amplifier.
Current amplifier.
Yeah, I believe it was just the last example before we went into the review.
Oh, the example, yeah. This example?
Yeah, it was just before the simplified, or before the small signal model. It was the first model.
You mean this?
Okay. Would you? Yeah. Sorry, that was my dog. Yeah. Just a quick question behind this was: will you put in because you're saying to find the output current and the input current? It was for that reason that we could assume though this is a current amp. It was that reason we could assume it's a current amplifier. Under other conditions, we might assume this was a voltage amplifier still, right?
We can still find the voltage. Do we find the voltage on the output or not?
I don't.
Yeah, I guess we don't. But both these I/O, because I/O is basically I emitter which comes here, and we can relate it to the current. Yeah, this current goes through RC2 and RL. Both are in parallel, and we can find the output voltage by multiplying that I out to RL parallel RC2 in this case, because let me see the original circuit. Yeah, you see, if we're looking at voltage out here, when we have the RL would be in parallel with it. And then on the input side again, RS, we can multiply the IS by the IS by the RS. Okay, and you would get VO over VS.
Thank you.
Yeah, you're welcome. Okay, any other question related to this? If not, yes, good guess, another me. Sure. Thank you. Kishan, question?
Oh, so can you hear me?
Yes.
Okay. Can you go over the what was it? R11 and R22, like for the shunt and series circuit, the look and short one, the last one.
The last one, R11 and R22 is right here. Yeah,
below that, it was look and short, I think, for the shunt and shunt series.
Are you talking about this circuit?
No, I'm talking about slide 12.
Shunt series?
Slide 12. No, below that.
I don't have the number here, but can you tell me it's not? This is shunt series.
It's in the same PDF. It's almost in the middle.
So tell me where.
Okay. Keep going.
We
Keep
finished that
going.
exam.
Yeah, keep
Oh,
going. Yeah.
good, going.
After this slide, yeah. After this.
After this,
One below that. One below that. Yeah, this one.
okay.
Yeah. So look in here and open and short. Like, can you explain the whole thing again? Like that.
Okay. So for this one, which is series shunt topology, right?
Yeah.
We realized that when we have series shunt, the feedback network is the nature of the feedback network is H parameters, two-port network. Okay, and for that, R11 was H11, and for H11 we had to short V2 when we were dealing with H parameters. R22 was H22. We were looking into the port 2 of the H parameters, and in order to find that, which was V2 over I2, we had to keep V1 open. Okay, so this is the kind of thing that could we had to memorize somehow. Either the equations or I can write it out, but it takes time. If I sit down and want to bring it from my mind on a piece of paper, that H parameters, writing the equations, then finding H11, H12, H21, H22, and so on. But this technique would eliminate all that hassle. Basically, to find R11, you know where you are looking in. You're looking into this side, right, to the left-hand side. So the left-hand side corresponds to series. Right-hand side corresponds to shunt. Okay, so you're looking into the series side, which means in the first port. But you're wondering, what do you need to do with the other side? And the answer is to short. But to relate that to our topology, when we see that on the output side we have shunt, we say that, this shunt brought the short, okay, for R11. And anywhere, either on the input side or the output side, we have shunt, we will short that side in order to find whatever we are looking from the other side. And as far as data is concerned, on the input side of it, which is this side, we want to know if we need to keep it open, which means we need to consider voltage, or short it, which means we need to consider current. Okay, but what we need to do, again, we follow whatever this says, the first part, series. So series meant open. But just for the data, on the output side, shunt is translated into voltage source. So we either have a voltage source or a current source out here, right? But shunt, remembering shunt means voltage source, then we know that it is this voltage over this voltage as the data that we need to find. So there's nothing that you need to know about the two-port networks like that using this technique. And it basically helps you in finding R11, R22, and data for all these cases, for each case. So,
Yep, makes sense. Thank you.
Does it? Okay, I was going to show you this one and see if you can follow.
Yeah, I can follow through the look and open and short. Yeah, table.
Okay, great,
Thank you.
great. Thank you. Any other question? This was feedback, and you know a lot about feedback. However, at the end, it boils down to your ability of analyzing circuits. It's more your techniques that you've learned in your introductory electronics. So you need to be able to draw, analyze these type of circuits, and the DC analysis and stuff like that, that is more of a factor in getting really a circuit with feedback analyzed. The general trend of it is simply summarized here in these slides here. Okay. But when you short this, for example, what is it that you're seeing from the other side is your ability of analyzing that circuit. Usually the feedback network is simple, 2 or 3 resistances. It's not a big deal. But the gain of the newly formed amplifier is what is most challenging. Okay? So we need to go again and review everything that we learned in the introductory electronics to make sure that we can use that knowledge in analyzing the amplifier part of it, at least, you know. If we can do that, we can do the rest of the things. The rest of the things are way easier than that. All right? Any other questions? Anyone? So I want to get into something which could be more interesting to you guys. Everything we talked about for amplifiers was under negative feedback. Now, what happens if we have positive feedback? And that's where feedback and stability come into the picture. So when we had this system, you know, this is the feedback block diagram. We came up with a gain under feedback, which was the gain without feedback over 1 plus k beta. That we must remember it by heart now. However, if this negative that we had would turn out positive, what we would get in the denominator would be 1 minus a beta. Now, if a beta would become 1, this could go to infinity. And going to infinity is not something definite, right? So it's what we, in electrical engineering, we call it a chaos. And in fact, this condition plus the positivity of the feedback are the 2 conditions that we can get a circuit to oscillate. Okay, so it becomes an oscillator. So far up here, we were talking about a feedback network that could amplify for us. An oscillator has nothing to do with amplification. I mean, it does, but there is an amplifier in here, but the performance of that circuit is not an amplification. It's an oscillation that we feel, you know, the signal keeps going up and down, up and down. So basically, this is the denominator that causes that. You see, this negative here screws things up. However, this would never get 0. 1 plus something which is positive itself can never get 0. That's why negative feedback guarantees that you have a stable system, not chaotic. Now, most of the systems they have 2 poles. And if you remember, poles meant that, you know, there are the points or the values for which this denominator can go to 0. Okay, they were called poles. And if you have 2 poles, we have 3 possible response of the circuit. One is that, you know, the circuit can oscillate and die out. The other one is that the circuit can oscillate and grow to infinity, which is very bad. And another one is that if we could keep the the poles on the imaginary axis, then it would actually be equivalent to a sinusoidal wave. So the oscillations would stay as it is. It won't die, it won't grow. Okay. So in fact, they use this property in order to make an oscillator. So if your poles are on the imaginary axis, then you have an oscillator. And if you want to avoid an oscillator, then your poles must be on the negative side and on the real side, actually, on the real axis. Okay. Otherwise, you will have oscillation. However, that oscillation dies out. So, in order to basically stabilize amplifiers, there are techniques that we use, and we change the behavior of the circuit such that it becomes more stable. Now, one of them was, again, when we did the negative feedback, and that was by pushing this frequency, the pole that we had out and outer. That was for single pole system. But when we had more than one pole, so this black curve is an amplifier which has more than one pole. So it is at least two poles. Okay, and in two poles, we realized that we could go crazy. If we want this circuit to amplify, we better not let it get into any situation that could cause oscillation. And that is by introducing a capacitor between the output and input. This capacitor between the output and input of the amplifier follows the Miller effect or Miller theorem. Remember, in Miller theorem, what it would do, it would introduce a huge capacitance on the input side. The side effect of that huge capacitance was reduction in the bandwidth, and it was considered bad at that time. But if we have an unstable amplifier, we better have a stable one, but with lower bandwidth, smaller bandwidth. So the effect of this capacitor is a filter that it makes with the dominant pole, which that dominant pole makes this multi-pole circuit look like a single pole circuit. And a single pole circuit does not go through this problem like that. This is for two poles. If you have single pole, basically you have only decaying in time if you have any RC. Remember, RC was single pole. So in terms of the frequency, there will be only one pole, but that one pole guarantees that we're not getting into oscillation. So this is called frequency compensation. If you remember, in a number of circuits that we did study, and as an example, the two-stage CMOS amplifier, there was a capacitor from the output of the second stage to the input of the second stage, and that was the purpose of it. And I said, we'll talk about that later. So this is compensation capacitors, DC. Okay. So basically, when we have a system like this, if our loop becomes one, then we are in trouble. So when the magnitude of the loop becomes one, while the phase is such that we have a negative here. How was the phase causing negative here? If you go back to this original thing, we had a positive. Positive means no phase difference. So it means that around this loop, all the signal is having the same phase. Same phase means either 0 degrees or 360 degrees. Okay? So if we manage to feed back our output to the input with 0 degrees or 360 degrees, at the same time maintaining this condition. So these are the two conditions that are have the name of Barkhausen criterion. That's for the name of the person that theorized it this way. So the Barkhausen criterion says that we have magnitude of the loop gain. Loop gain, remember, A data was loop gain. If it is 1, and you can you can imagine that when we say AS beta S, that means they are both dependent on frequency. So there is a place in frequency that this multiplication can have a 1 value. Okay, and if at the same time we have a 360 degrees phase difference, then we will oscillate. The circuit will oscillate. Okay, even if there is no input on it. So even if we turn off the input, this feeding back positive causes an oscillation. Now, for amplifiers, we come and analyze the loop gain, both in terms of the magnitude and in terms of the phase. When does the phase become 360? When we can introduce an additional 180 degrees, usually by the two poles that we have in the amplifier. Most of the amplifiers, most amplifiers do give you 180 degrees phase difference from their input to the output. So if we provide another 180 degrees phase difference through the data, we are providing actually 360 degrees phase difference, or 0. And that is when the danger of oscillation can become real. So in order to be able to avoid that, we have a couple of definitions, to analyze how far we are from the risk of getting our amplifier which has 2 poles. Okay, what's the risk of it becoming an oscillator? And we define 2 margins. One is the gain margin for magnitude 1. The other one is the phase margin for the phase of 0 or 360. So for the gain margin, it is the gain, the difference that we have in the gain until it becomes 1. 1 means 0 dB. In dB, it is 0. So the difference that our gain has with the 0 dB, which is the horizontal axis, in magnitude, that is referred to as gain margin. And the difference that we have in the phase until it becomes 180 degrees, that is called phase margin. So these two tell us how far we are from making these two cases a reality, which risks the amplifier to perform as an oscillator. Aidan, question?
Yeah, I'm still, if you could repeat, I'm still a bit confused of two things. One, how going through the circuit, how going through the feedback loop in positive is applying that type of shift compared to what the shift is doing when it is negative. And my one other, if it's negative, is it still, if it's a negative feedback loop, does that mean it's zero shift because it's adding 180 and then assuming it's minusing 180?
But if we are, okay, let me draw here. Oh, I have to bring it over my laptop. Sorry, just a moment. You still see that, right?
Yeah.
Okay. So, when we say that, say we have an amplifier, right? This amplifier, let's go to our old friend. Non-inverting op-amp amplifier, right? You see, when we have this negative here, it meant that our output is already 180 degrees different than this input. So that 180 degrees would make it negative feedback. Okay? Now, if we had something here that it would introduce an additional 180 degrees, then our output, whatever our output phase was, would be the same on the input side. That would cause a positive feedback. In fact, that was the reason that we never used positive terminal when we were feeding back from the output to the input. So we could never flip around the op-amp and use positive terminal getting into the negative feedback, getting into the feedback, because that would mean a 360 degrees phase difference. If the output goes up, this input also goes up. And that would cause trouble. It would not amplify for us. So if we had means of introducing another 180 degrees in this case, which we can, every RC, when you have an RC, you have a phase difference. Every RC can introduce 90 degrees of phase difference, right? A maximum of 90 degrees. Okay? So, ideally, two of them back to back will give us the 90 degrees. But in reality, three of them, and each introducing 60 degrees, would give us a total of 180 degrees. I don't mean to confuse you guys, but so let me suffice to this. I think your question was that, how would we get 360 degree back? It's basically, in this case that we have resistances, never. If we are careful and we use the negative input terminal in the feedback, never. But if these were not pure resistive, then we could get some phase change. And if that phase change adds up to 180 degrees, we have an additional 180 degrees to the original 180 degrees. And that gives us 360 degrees, or zero, which would make this condition become true and this condition. System. And now, if our gain is 1, which that is at least 1. If it is even more than 1, it can still continue to cause trouble and oscillation. It doesn't have to be exactly one. But but based on what we have here, definitely for 1 and 360 degrees, we are getting oscillation, not amplification. Okay, and that is due to the positive feedback that we are introducing in our loop, rather than the negative feedback. Does that clear things a little? Let me tell you what, oscillators is a field for itself. My PhD was on oscillators. Okay, so it's a complicated subject, to be honest. But put it simply, I mean, I couldn't make it simpler than this. So it's just due to the positive feedback that we get, and when this gain is become 1. Okay.
I'm just trying to, because there is a few parts where it seems like I guess I'm having some gaps in some knowledge.
Yeah.
To compute.
Yeah.
And,
no, you have all the right to have lack of knowledge, because this is basically very short. Yeah. And I tell you what, on the exam, I'm not holding you guys responsible for this part. Okay. So don't worry if you don't get your.
For most of it, the idea of having the phase shift is allowing it to basically sort of either subtract from itself or add on to itself, and that's how it's sort of balancing. And if it's adding on to itself constantly, you're going to have, like, because the only problem that I sometimes get is with when it becomes perfectly oscillating, or how it translates to oscillating. Because I understand it from the perspective of the complex domain, but from the perspective of translating that directly to a circuit, sometimes I still have a bit of issues, because I remember positive feedback as more of directly going out of control, because it would have that ever expanding. But just relating it directly to the circuits, I'm still having some disconnect.
But yeah, this you mean, and that's exactly true. Unless you can control the gain such that what does this K data equal to 1 mean? Where is it? Here, K data equal to 1. It means the same amount that you are amplifying, you have attenuation in your beta. And remember, beta was a network that was taking the output and sampling it, bringing it back to the input. Now, this sample is, if the sample is exactly reciprocal of the amplification, then the loop gain, and this is the loop gain that we are talking about, L of it, becomes 1. And for the frequency that this has happened, the gain is 1, and the phase has turned 360 degrees. That's the frequency that you can expect the oscillation. Okay. So I just wanted to give you a taste of what happens if we don't manage to have negative feedback. And in fact, there was an old electronic joke, they were calling it, which I have to think exactly to see if I remember it right, but it was like, all the amplifiers oscillate, but oscillators amplify, something like that, which wanted to say that it is easy to lose the control over a circuit. You're designing an amplifier, but if you're not careful, somewhere, and you're using negative feedback to stabilize things, but somewhere in your loop, you are making it to turn around to 360 degrees. Oops, we are going above the time, and if you guys are here, let me have another me, please. Yeah, go ahead and type me. Thank you. But yeah, so